the introduction, and thank you so much for having me. Yeah, so today I'll be talking about basically, do language models know when they're hallucinating? And yeah, so this is my summer internship work with Microsoft Semantic Machines in collaboration with Ben, Jason, and Chris at Microsoft. Yeah, so I'll get started. So before I sort of dive into the details, I'll give sort of a brief overview of the interactional context that we're interested in. So this is, in technical terms, just retrieval augmented generation, which is something, just think of like Bing Chat, right? Where a user like chats with Bing, and then the ask like a query, for example, like, oh, what kind of food is Bali most known for? And then the system in the back end sort of does like a web search looking for like related terms, such as like food in Bali, returns a bunch of web pages, and then there's a large language model in the process sort of generating a response to the user's query based off of those web pages, based off of sort of the results that are retrieved from the internet. So how this works in search results is that the search results are sort of stuffed into the prompt of a large language model, where just in text form, it's something like just like web search result 1, web search result 2, where like the texts of these web pages are stuffed into the prompt. And then it asks a large language model, okay, based on the data sources above, answer the user's question, something like that. So like, what are the best food in Bali and things like that. So why do these systems do this? So like, instead of just like asking a large language model, what is the best food in Bali? Why does it sort of ask, why does it do like a web search and then sort of generates an answer based off of that? So like this web searching and generation process is generally more preferable than say just like asking directly a question to a large language model, because oftentimes information is fluid, it can change over time, right? So instead of like having to retrain a large language model, which is like billions and billions of parameters for millions of dollars, if the web search reflects this updated information over time, for example, if suddenly the best food in Bali becomes, I don't know, carbonara from Italy or something, then the web search result would be more likely to reflect this updated information. So you can just use the same large language model to sort of generate that instead of having to retrain it from scratch. So obviously there are many considerations that we want in such a scenario, right? We want what's ultimately generated by the large language model to be accurate and to reflect the data that is present in these web search queries. We don't want, for example, a web search query to say, oh, the best food is, I don't know, is rice. And then the large language model returns to the user and says, oh, the best food is, it's not rice, but it's chicken or something like that. Like, we don't want that. We want what's ultimately generated by the large language model to be faithful and to reflect accurately both user intent, but also the underlying knowledge here. So this sort of goes into this problem of hallucinations in large language models, right? Where oftentimes large language models will just, they'll make up stuff from yeah, they'll just make up random things and not really sort of accurately do what the user intended it for it to do. Or in this case, it will just make up stuff and will not accurately respond to the question based on the knowledge in the given knowledge source. So this problem is called sort of hallucinations, whereby hallucinations are just generated responses that are either incoherent or unfaithful relative to information given in the prompt itself. And traditionally, this can be really seen as like an entailment problem, right? Where if something that is generated, if a claim that is being generated does not entail the information provided by the information source, then it is considered to be a hallucination, right? We want ultimately what's being generated to accurately entail and reflect the information that is returned to us in the web query, in the search results. So a very simple example of this is, for example, if you ask a large language model to paraphrase the phrase, apples are crimson, right? Here, in this case, apples are crimson are sort of like, it's like the grounding knowledge source. It's what we want the large language model to base its response from, right? We want to paraphrase this certain text. So here, if the large language model sort of responds with, okay, apples are red, then that is considered to be great. That's faithful, right? Because it's doing what we asked it to do. It's saying that like crimson is a shade of red. It's recognizing that crimson is a shade of red, and it's doing what we want it to do. So that's great. But if instead it says something like apples are green, well, then this is bad, right? Because the knowledge source says apples are crimson, and crimson is not a shade of green. Crimson does not entail green. So, it's doing something bad here. And we call this a hallucination. And there's like many types of hallucinations, intrinsic, extrinsic, that doesn't really matter. But for example, if it says like tomatoes are red, well then, okay, yeah, tomatoes are red, but this phrase can't really be naturally entailed from the phrase apples are crimson, right? Nowhere in here says tomatoes. It's making a claim about tomatoes that is not entailed or grounded in the knowledge source. So this is bad. So, here you might see that, like, yeah, while models may leverage latent knowledge, its internal knowledge, to inform their responses, such as recognizing that crimson is indeed a shade of red here, oftentimes directly stating this knowledge in a response. For example, if here it generates crimson as a shade of red, is oftentimes considered an extrinsic hallucination. It's like a hallucination, as it is neither entailed or contradicted by the source, right? Like crimson is a shade of red is not entailed or contradicted by the phrase apples are crimson. So here, really maintaining grounded generations for large language models and avoiding hallucinations involves a delicate balance of retrieving and manipulating the knowledge that the large language model inherently has or has gained, both from its weights and the given context itself. So, hallucinations, there are, we ultimately want to reduce hallucinations in a lot of these scenarios. But in order to first reduce them, we first need to be reliably able to detect when large language models are indeed hallucinating. So how have people traditionally done this? People have tried many things over the years, and not all of them are great. So, people have begun sort of this task of like detecting hallucinations by looking at lexical overlap metrics, which is essentially like here, like, okay, if it says apples are red here, well then in the information source, apples and are both present in the information source, right? There's only one word that is not present there. So here, you can train a very simple thresholding classifier to say that, okay, if like 90% of the terms that are generated in an output are present in the information source itself, then, okay, let's say that is not a hallucination, right? But the thing with this is that these lexical overlap metrics, they promote a lot of sort of repetitive generations. And oftentimes they're not the best at detecting hallucinations. For example, apples are red and apples are green both have 2 out of 3 terms present in the information source. But one of them is a grounded generation, what we want, and one of them is a ungrounded or hallucinatory generation, which we don't want. And well, just based off of lexical overlap metrics, it's very hard to detect to discern rather if one of them is a hallucination or one of them is not, because 2 out of 3 terms for both are present in the knowledge source itself. So lexical metrics are pretty bad, right? Then people have found like, okay, well let's try using other models to detect if a generation was a hallucination or not, right? Because hallucination is it can be defined as entailment, right? Where if a generation is entailed by the knowledge source itself, then that's not a hallucination. If it's not, then and entailment in NLP it's been a pretty long-standing task of trying to detect textual entailment. And there's like a bunch of other models that look at like, okay, can we determine if like 2 sentences entail each other, contradict each other, or have no relation to each other? So people have thought like, okay, well, why don't we just use these off-the-shelf entailment models, and we just like ask it to classify these generated responses versus these knowledge sources, and to see if they're hallucinations or not. So that sort of worked better, but with the caveat that a lot of these traditional entailment sort of models, they only really train on single sentence paired entailments, right? Like if you look at like single sentences, it's very easy from a human perspective to just like see like, okay, yeah, apples are crimson, this sentence entails this sentence. But if you extend that to actual like Bing chat responses, they're going to be like maybe hundreds or thousands of words in a single response. And then it becomes exponentially intractable for these models to sort of try to do this task, right? It's no longer only looking at single sentences, it's looking at like paragraphs and paragraphs of texts and trying to tell like, okay, does this 1,000-word response, is this entailed by this 10,000-word web search query, right? And it's very hard to do so. So here, people can't use really these traditional single sentence entailment models. So they have to rely on these billions of parameters of large language models, which originally generate the response. So instead they had to build these billions of parameters big language models and try to do this task of detecting hallucinations. And then it becomes really computationally expensive to do so, right? Because you're having to run these large models so many times just to detect if something is a hallucination or not, which is very expensive from a sort of production use case standpoint. So like, okay, so our motivation is like, can we both reliably detect hallucinations, but also can we reduce the cost of doing so, right? We don't want to retrain this whole other model just to detect if something was a hallucination or not, right? We want to do this task both with better accuracy, but also with better computational performance and less complexity. So our research motivation here is like, okay, can we do this from language model internal states? And I'll go into that a bit later. So in this area, people have found that large language models, because they contain these billions of parameters, it's very hard to accurately say like what each component of a large language model actually does, right? Like we know what the transformer architecture does from a mathematical standpoint, but then these large language models, they have these massive blocks of these transformers. And they extend these transformer blocks into like layers, like 40, 80 layers. And then suddenly it's very hard to tell like what each actual part of these large language models are actually contributing to the final generation behavior of a large language model. So this sort of came with this sort of began the field of like mechanistic interpretability, which is like people looking at like, okay, people trying to explain like this part of a large language model contributes this way marginally to its final behavior. So in this line of research, people have found that you can in its billions of parameters, you can precisely locate where large language models store facts that they have seen before. So for example, a fact would be something like, like the Eiffel Tower is in Paris, right? And you can locate from its billions of neurons, which neurons actually store these facts inside the large language model's internal states. And the consequence of that is that you can actually modify this behavior. If you can locate it, you can sort of change that fact to make the large language model generate or think that, instead of the Eiffel Tower being in Paris, you can make it think that the Eiffel Tower is in Berlin or something. And then it will use that fact in across a variety of contexts to generate like, if you ask like what country is the Eiffel Tower in, then it'll say Germany because Berlin is in Germany. So then it maintains this generalizability and specificity across contexts. So you can really isolate precisely where facts are located in the large language model's memories. So on a similar vein, it's like, okay, can we do the same for hallucinations, right? Can we locate where the signal almost of hallucinatory behavior when it's sort of like making up random stuff within a large language model's internal states? And can we sort of try to mitigate that? Can we detect that? Can we mitigate that? Can we sort of bias the large language model away from like generating random stuff instead of like generating accurate, faithful things in its generation? So sort of on a similar vein, we're like, okay, can we do this for hallucinations? So the setting that we're looking at, just to formalize things a bit, it's like, okay, we're given an interaction history, a knowledge source, an instruction, and a conditionally generated response. And ultimately, we want to probe the large language model's response to detect if, okay, does the response contain a hallucination or not relative to the instruction and the knowledge, and to a lesser extent, the history itself. So we do this task of trying to detect hallucinatory behavior across a variety of tasks. and a variety of domains. So we look at like summarization, we look at like dialogue, we look at data to text. For abstractive summarization, we look at the data set CNN Daily Mail, which is like, it's essentially, it's just news articles from CNN and Daily Mail. And we ask like a large language model to just like generate summaries for them. And we probe sort of these summaries to see whether or not they're faithful relative to the articles themselves, things like that. For dialogue, we look at Confever, which is it's like a Wizard of Wikipedia dialogue task, where essentially you have like two people talking about something. For example, here they're talking about like Murray, like the tennis player, and then it's like suddenly in the middle of the conversation, a speaker has to ground. A speaker asks a question, which is like, okay, like who's part of the big four in tennis or something like that. And then the other speaker has to sort of like search Wikipedia, trying to answer this question. Like, okay, so it searches like tennis, it searches like big four, and it finds like a paragraph that says the big four is like Nadal, Federer, blah, blah, blah. And then sort of it has to base its, and the speaker then has to sort of base its next response to the other person based off of this knowledge source. So then it sort of says like, okay, part of the big four, there's Nadal, there's Federer, blah, 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 things like that. So it's like it sort of has to ground, the person has to ground its response from this information source in Wikipedia. And then for data to text, it's essentially just a data set of like restaurant descriptions. For example, there's names, there's like types of restaurants, the customer rating of the restaurant, and things like that. And then essentially the task is like, you have to generate a natural language description of this restaurant based off of these attributes. So like here, it generates like a restaurant description based off of these attributes. So based off of these three texts, we look at hallucinatory behavior in two different ways. So one, we look at these things called organic hallucinations, which is essentially we ask a large language model to do these tasks themselves. So like we ask a large language model to generate summaries for CNN Daily Mail. We ask a large language model to generate dialogue responses that are grounded in the knowledge source, or we ask a large language model to generate these natural language restaurant descriptions based off of these attributes. So we ask the large language model to do these tasks, essentially. And then we label these tasks, we label these generated responses from a large language model for hallucinatory behavior. In addition, we also look at sort of synthetic grounding errors, which is like, okay, like given the ground truth ground truth responses to these tasks, right? Like if we look at the actual article summaries of CNN articles that are provided in this data set, can we sort of tweak them a bit to make them sort of ungrounded? Can we sort of tweak like a sentence or two, a word or two in these news article summaries to make it such that the summary, this edited summary, does not accurately reflect the actual content in the news article itself? So we sort of not only ask large language models to organically to generate a bunch of things, but we also ask humans to sort of like create these synthetic grounding errors to see if like we can detect for them. So some examples of organic hallucinations are here. So for example, the first one is abstract summarization, where it's like the news article has a knowledge, like a sentence in it that says, oh, there's like 6 to 9 hurricanes. And Llama 2, our large language model, generated 6 to 11 hurricanes. So obviously that's bad, right? That's a hallucination, because like, where did it find 11 from? So we asked humans to sort of label for like the spans of where the hallucinations are in these large language models, if any. So we do that for summarization, we do that for knowledge grounded dialogue, and we also do it for data to text. Like for data to text, right? It's saying, oh, this restaurant, the Wrestlers, is located by the riverside, which is like it's not present in the knowledge at all. So it just came up with that on its own, which is bad. It's hallucination. So in this annotation, right, we ask humans to really annotate for like where they think the hallucination is in their response. So in this annotation, we find that humans don't actually 100% agree on what the exact span of hallucination is in their response. which is like it's expected, I guess. For example, here, two humans thought that the hallucination was like the taxi driver or this entire sentence. And sort of we ask humans to label for the minimum spans of hallucination, right? Like what are the minimum number of words or spans of text that you have to edit or delete in order to change a response from a hallucination to a grounded one. And you can do this in a variety of ways, right? You can either change like the taxi driver to something else, or you can just like delete the sentence in its entirety. So there's sort of a reasonable amount of human disagreement there. So here, for example, people think that like the high rated is a hallucination, whereas the second annotator thought it was only high. Like if you change high to low rated, then suddenly it becomes grounded, right? So there's some variety there. For synthetic grounding errors, we follow these distinct taxonomies of sort of hallucinations and grounding errors to sort of create these minute changes to the ground truth reference outputs of these tasks in order to make them ungrounded. So here, for example, this is a CNN Daily Mail article where it's like, okay, this is the article text and this is the summary. So a minimum change is like if you change homegrown to foreign players, then suddenly this becomes a contradiction to what the information reflected in the article itself, right? And it's like we follow sort of these pre-existing taxonomies of like how do you change these sort of summaries in order to make them ungrounded. And you can change it by like changing predicates, you can change entities, you can change the times, you can change co-reference things, about a bunch of ways to do that. And we follow sort of existing taxonomies to induce these synthetic grounding errors in reference responses. So some examples are like, if we change the knowledge source from like the most significant cultural, like Elvis Presley was the most significant cultural icon. If we change that to the least well-known musician, then suddenly, that's an error, right? That makes this response an error relative to the knowledge source itself. So here, if we delete like pub, then suddenly this restaurant description that says Clown's Pub is suddenly a error relative to the knowledge source. So we do that for a bunch of tasks. So in our span level annotation of hallucination, we ask like, okay, how much do annotators actually agree in this task of labeling for hallucinations? So in order to do that, we sort of create this, we create this new like partial credit F1 measure to sort of measure into annotator agreement, which is essentially, it's like, okay, given each annotated span of hallucination, how many tokens in one annotation is also labeled to be a hallucination in the other annotation as well. So this really treats spans as sort of the most important units of annotation and not so much tokens. Like if you look at the token-wise overlap between two disagreeing annotations, then for texts that are very long or that have a lot of tokens, then that sort of outweighs other texts with lower amount of tokens, and that sort of distorts the span level inter-annotator agreement. So here with this measure, if we look at span, if we treat spans as the units of interest, then this really sort of normalizes things a bit between texts of different lengths, different sizes, things like that. And we find that, annotators generally agree pretty much on where sort of the locations are in the hallucinations. So we get like, we get inter-annotator agreements around like 0.6 to 0.7, things like that. So now with this data set, then now it's about like, okay, how do we detect hallucinations from this data set? So we do this via probing, which is just looking at the internal states of large language models as they generate as they generated something relative to what was prompted. So here, right, like we provide the history, the knowledge, and the instruction, and then we ask it to generate a response. So what an autoregressive large language model does is essentially it just like it goes over every single token and then does next token prediction. It's like, okay, given what was already previously generated, what's the most likely token next, right? And it does that until it sort of stops. So here it's like it's going over the history, it's going over the knowledge, it's going over the instruction, and then it's like, okay, given this, what is the next token? What is the most likely token? So it says, indeed, okay, now given this, what is the most likely token? So you can think of this as greedy decoding. There's also other decoding methods, things like that. But an autoregressive large language model essentially just does next token prediction. So here we look at like, okay, what is the state of the large language model as it generated each token in the response? So we're like, okay, what was the state of the large language model as it generated this token, this token, this token, this token, this token? And what I mean by state here is really looking at all its layers, all its parameters of the large language model as it sort of proceeded over the generation. So here it's like, okay, what is the self-attention value of the layer 0 of this large language model as it generated this token, as it generated this token, as it generated this token, things like that. So what this practically means is you have vectors, you have like thousands of numbers in a vector times how many tokens of response times how many layers. So you have like billions of parameters. This is where the billions of parameters of large language models actually come from, right? So we look at these internal states of large language models as they generated each single token. And then what we do essentially is we create single layer classifiers, looking at like, okay, given this state of the large language model as it generated this token, can we predict if this token was a hallucination or not? So like for this one, it's like, okay, given the self-attention layer 0 of this large language model as it generated this token, can we predict if it's a hallucination or not? And practically speaking, this is just like for us, because we use Llama 2, it's like around a 5,000 something number vector. And we just do a single layer classifier, like based off of these numbers in the vector, can we predict if it's a hallucination or not? Yeah, and then so that you can do that for single token predictions, or you can do that for response level predictions as well. So it's like, okay, given all these states in a generated response, can we predict if the response contained a hallucination or not, or if it didn't contain a hallucination, things like that. So we can use this to really probe into the behavior of a large language model for hallucinations. And sort of this image is just like, it's sort of an illustration of our probes working in practice, right? So here, think of this as like a response. These are the tokens in the response, token 1, token 2, token 3, all the way to the last token on the x-axis. And these are the layers of the large language model. So here, there's like 80 layers in this large language model. And sort of these sort of colors, these little blocks here are our classifiers predictions of whether or not the token contained a hallucination or not. So here, this box here is sort of like the ground truth, the annotated span of hallucination in this given response. And as you can see, sort of these predictions almost match the ground truth annotated response of hallucination. So you can sort of see this sort of working in practice. And we try a bunch of probe classifier architectures, looking at like response level, token level, supervision. We try like linear layers, attention pooling, a bunch of things. So in terms of performance, right? Like how does probing the hidden states of a large language model actually, how does this actually do in detecting hallucinations compared to pre-existing state-of-the-art methods? We find that we beat a lot of the methods. So essentially, people have, these are just like a bunch of baselines looking at like, oh, the sequence log probability of the generated response, or like, oh, if I create this question answering model, trying to detect if something is a hallucination or not, like how does that do? And we find that, our little classifiers, just looking at the information that is already pre-computed during generation for a large language model, just looking at that information itself, you can already pretty good, pretty well. You can detect hallucinations already to a very performance degree compared to these methods that oftentimes use, they create another billion size large language model to do a bunch of fancy things. So this really looks at like, okay, we can actually tell if the large language model is hallucinating just based off of the pre-computed information. We don't need to compute new information. Again, we can just look at pre-computed information inside the large language model's behaviors. So then we looked at like, okay, like sure, generally this behavior, outperforms other state-of-the-art baselines, but then where is the signal of the hallucination actually inside a large language model? So this is really sort of the notion of saliency, which is like, okay, given this part of a large language model, how well can we detect if it's a hallucination or not, versus if we give it a different part of a large language model? So here we look at like sort of the layers of a large language model, and like how each layer's hidden states are conducive towards predicting whether or not it was hallucinating or not. Like where is the where's the signal almost of hallucination within the large language model's hidden states? So here, there's layer 0, layer 40. We find that generally across tasks, it seems like the middle layers of a large language model are where sort of the signal of hallucination is the strongest. So, if we just use like the 0th layer of a large language model and try to predict if it was hallucinating just based off the numbers there, then that doesn't really do well. But if we provide something like middle layers, then suddenly it like the signal of hallucination is much more prevalent in these middle layers compared to later layers or earlier layers. And that draws parallels into some prior work looking at like how semantic information is most salient in the middle layers of a large language model and in deeper layers. This really tells us like, okay, we might not need to compute information over all of the large language model. We can just really look at a single layer, and that massively reduces the computation needed to detect if something is a hallucination or not. And then we look at sort of the saliency of different types of hallucinations. So hallucinations are mainly like two types. So in the traditional entailment framework of defining hallucinations, intrinsic hallucinations are generations of a large language model that directly contradict what was sort of provided to it. So like, for example, if I say that apples are green, when provided with the context of apples are crimson, then apples are green, that directly contradicts with this knowledge source. So that's for like an intrinsic hallucination. Whereas extrinsic hallucinations are just like, if I was provided a knowledge source about apples and I say something completely different, if I say something about tomatoes, then that has no relation to sort of what was provided. So we find that sort of intrinsic hallucinations are slightly they're easier to detect in a large language model, internal states, which seem to mean that like large language models sort of quote unquote know when they're talking about something else better than when they're directly contradicting something that was already said. So this really looks into sort of the different behaviors of a large language model here. Then we also test if this behavior sort of varies across different model sizes. Because like Llama 2, right? There's like 7 billion, 70 billion, 40 billion sizes. We look at like, okay, does this behavior actually vary across large language models of different sizes? And we find that not really. There's not really a statistically significant difference between detecting whether or not a large language model was hallucinating based off of its internal states for models of different sizes. So that this possibly has to do with the way that these large language models are trained, as in the 7 billion versus the 70 billion version of these large language models, they're trained in very similar ways. They're trained using the same data, the same architecture, general architecture. It's just the amount of parameters that are different. So perhaps we think there might be something to do with sort of training data and sort of training processes that has an influence on how easy it is to detect whether or not something was a hallucination or not. Then we look at sort of like ecological validity of synthetic grounding errors. So like in prior work, people have tried to detect hallucinations by creating these massive classification models on manually created synthetic grounding errors. So they're like, okay, I'm going to ask like a bunch of humans to create as many errors as I can in a summary of an article, and I'm going to train a classifier on these manually edited summaries of articles, and I'm going to train this classifier to predict if this article was an accurate and faithful representation of the article's text itself. And people have done that for a long time, and we find that that's not really valid when detecting hallucinations, right? Because a large language model's way of hallucinating is very different from how humans sort of create these manual grounding errors. Humans may think that, oh, if I edit a single word, then suddenly this summary becomes unfaithful relative to the article itself. But for large language models, they behave in very different ways from what humans traditionally expect. So these traditional paradigms of like, okay, let's ask a bunch of humans to create this ungrounded, unfaithful data set and try to use that to determine if a large language model is hallucinating or not. That doesn't really work when we sort of use it to detect if large language models are actually hallucinating or not. So for future work directions, we hope that we suggest people to sort of look at actual organic large language model generations rather than sort of create sort of these synthetic grounding errors from the ground up. Because oftentimes training on these synthetic modalities don't really translate to organic hallucination detection, which is fundamentally what we want for production level scenarios. Also, we look at sort of cross-domain training, which is like, okay, if we train a probe to detect hallucinations on a factor summarization, how well does this probe do in detecting hallucinations for knowledge-grounded dialogue, things like that? Like, is there a consistent signal of hallucination across domains? And we find that, at least for our tasks, that there really isn't, or that we're not able to find that consistent level of hallucination signal across tasks. So like probes trained on like CNN Daily Mail, they don't really translate well to other tasks, and this is the same for all tasks as well, which suggests that there may not be a consistent signal of hallucination for large language models across domains. But this is very uncertain. We might have to do more cross-domain training, such as like a FLAN T5 model, where you do like 1,000 different tasks, and then you try to generalize to new tasks, domain, things like that. That might work, but at least for our purposes, we don't really find a consistent level of hallucination. So a consistent signal of hallucination across different tasks. So there's more future work to be done there if we want to improve probe generalization to novel domains. But yeah, in terms of the final contributions, takeaways, and future work, we create this data set of organic and synthetic hallucinations. We create a new probe method looking at the internal states of a large language model to try to detect if it's hallucinating or not. And we do a bunch of analysis and evaluation on looking at like where the signal of hallucination is, whether or not this is consistent across different modalities, different tasks, things like that. But yeah, our method for diagnosis, I'd say shows for the promise for mitigation, as in, it's pretty simple to create a mitigation tactic for hallucinations just based off of like these probe predictions, right? So like if our probe predicts that something is a hallucination or not, then, you can ask a large language model to regenerate, to sort of generate something that is not a hallucination, or you can use this probe as like a signal to bias the generation away from hallucinatory behavior and things like that. But also there's sort of like a question on like, can we get annotators to agree more in terms of like where hallucination is in generated responses? As we saw before, there really annotators presented some level of disagreement there. And like, is it possible to get annotators to agree more? And fundamentally, do these annotated labels accurately reflect the internal working mechanisms of a large language model as it generates something? But yeah, that's sort of the takeaways. And yeah, thank you so much.